All right. Hello, chemistry students. Welcome to our first session of virtual learning. I hope you guys are well. I hope everyone in your families are healthy. I'm doing well, my family as well. I'm seeing you guys already, and it's going to be a long few weeks because I miss you. But we need to continue learning, and so my goal over these next few weeks is to keep you engaged and keep learning chemistry. So today, our first video, just letting you know, we're going to start chapter 12. We're skipping chapter 11, at least for now. If time permits, we may go back to it, but I feel like it's chapter 12 is a little more important in your understanding of chemistry as you continue on in your science education. So chapter 12 is about solutions, and we're going to be talking about different types of solutions and their different properties, and there will be some definitions, some terms that may or may not be familiar. Some will, some won't, of course, as always. Build on what you've known, add to what you should know, and then we'll do some problems. And just the math, again, it's not complicated. There will be some formulas that you need to know, ways, and then you'll have to go back and we'll start talking about moles again. That doesn't go away in chemistry. But today we're going to start the first section. I'm going to try to lecture through section 12A. Section 12A covers mostly terms, definitions, and properties. There aren't really any problems, just a few, maybe a little bit one formula. But then section 12B gets into some of the ways of calculating concentration of solutions and how. So what that basically means is we're going to get to the point where we're calculating how many particles or how much of your solute is in your solvent. And that's going to make sense in just a second. So let's just dive right in. Let's get to some terms. I'm going to pull up my PowerPoint. You should be able to see me to the side and then my PowerPoint to the other side. And I've also posted the PowerPoint for chapter 12 in Google Classroom as well. It's already here. So if you would like to print those out and take notes as you listen to me speak, that's perfectly reasonable and possible, but either way, you're going to see them on the screen and you're going to see me. So I'm going to be over to the side, and hopefully this won't look too weird. And I'm going to get used to talking to the camera instead of looking out into the classroom where you guys usually sit. So I'm going to pull up my presentation now. Give me just a moment. All right, let me scroll back up to the top here, and here we go. All right. So solutions are a type of mixture. They're a type of mixture, but they are a special type of mixture. There are lots of mixtures that you're used to seeing. Trail mix, for example, is a mixture. And this, we covered this a little bit all the way back in the first couple of chapters of chemistry. We talked about mixtures. Mixtures are just things that are mixed together. But a solution is a special type of one of those. Like think about trail mix. If you have trail mix, that's called a heterogeneous mixture because you can see everything. You can see the cashews and the pecans and the almonds and the M&Ms and the raisins, et cetera, et cetera, et cetera. What the word homogeneous means, this word right here, homogeneous, what that means is that you can't see the difference. It all looks the same. Going back to that prefix, H-O-M-O, homo, meaning the same. So in a homogeneous mixture, it looks the same. There are two parts to a solution. You have a solvent. And if you're talking about liquids and solids, this especially works when you think about the way I'm going to say it to you, but it works other way, it works either way, no matter the state of matter. But a solvent is what does the dissolving. So it is what is most abundant in that solution. Now, again, sometimes you're not going to just, it's not just liquids and solids that can be solutions. And we're going to talk about all of that. So the solvent is what you have the most of in the solution. And then the solute or solutes, you can have more than one, is what's getting dissolved in that solvent. Those are the, if you think about a saltwater solution, I'll use that as an example quite a bit because we're all used to the idea of salt water. But if you're talking about salt water, it's the salt particles from the salt shaker or whatever into the water. So the water is your solvent, and the sodium chloride crystals would be your solute. They are getting dissolved in the water. Okay. Now, A few properties of solutions that we need to talk about. If you have a solution, a true solution, you simply can't filter out the solute particles. So if you try to filter out salt from a saltwater solution using something like a coffee filter, that's not going to work. It's just going to drip all the way through, and you're still going to end up with salt water in that beaker or the cup that you're draining it into. Solutes do not settle out of a solution. So what that means, if you have a true solution, everything in that solution is dissolved. You don't see any, for example, salt crystals on the bottom of the beaker. Solutions are uniform. That means it's the same throughout. You cannot see a difference from one side of the beaker to the other side of the beaker if we're talking about liquids in the container kind of thing. And there's no chemical reaction. There's no chemical combination. So when you make salt water, here we go again with salt water. When you make salt water, you're not chemically reacting salt and water. You don't create a new substance. You're just creating salty water, okay? And you can change the concentration of the solution. So again, back to our salt water example, if you want to increase the concentration of your salt and water, you can do one of two things. You can take out some water and keep adding salt, or you can just keep the same amount of water and add a bunch more salt, and you're going to increase the concentration of sodium chloride in that solution. I hope that makes sense. Again, as we're going, as you're watching this video, this is not a live video, obviously, but I'm going to, in the classwork or in the streaming portion of Google Classroom, feel free to let me know when you have questions, and I'll try my best to answer those, or also in our office hours time. All right, now there are different types of solutions. All right, we're going to start talking about liquid solutions, where the solvent is a liquid. And then, remember, that's what you have the most of. The solvent is what you have the most of. That's what does the dissolving. But then for liquid solvents, you can dissolve solids in them. You can dissolve other liquids, or you can dissolve gas in all of those. So all three states of matter can be placed inside a liquid solvent. And not every substance will work with every liquid. Not every substance dissolves in every type of liquid. So keep that in mind. But what are some examples of a solid dissolved in liquid? Well, salt water. That's, again, I've been using that a lot because we can all relate to that. But sugar water is also an example. If you're wondering about liquids dissolved in another liquid, well, that would be something like vinegar. If you wanted to make a vinegar cleaning solution at home or a bleach cleaning solution at home, you would take water, you would add a little bit of vinegar, a little bit of bleach, mix it all up, and then you have liquid and liquid, and you're not going to be able to see the difference in those. Okay, the water, you should have more of the water if you're making those solutions. Okay, water should be your solvent, and then you add a little bit of, say, the bleach or the vinegar, you add a little bit of that, and that becomes your solvent. Or gas dissolved in a liquid. That's soda, guys. Whether it's sparkling water or your Coke, Mountain Dew, root beer, whatever. If it's carbonated, that means carbon dioxide has been dissolved in that liquid. Okay. Now, when we specifically talk about liquid and liquid mixtures, there are two terms. We've got miscible. And what that means, what the term miscible means, is that the two liquids mix together and form a homogeneous mixture. So water and vinegar, you pour the vinegar into the water, you're not going to see the difference, and the vinegar basically dissolves into the water. Now, if you try to put two liquids together and they don't dissolve, it's said to be immiscible, meaning you can see, hey, there's the bell. Class would be actually starting now. You could see that the separation of the layers. So like oil and water, for example, are immiscible. You cannot make a solution with oil and water because the oil is always going to rise to the top, and the water is going to stay at the bottom, and the oil is just going to rest in the water. So certain liquids you can make solutions with, and certain liquids you can't. Let's talk briefly about solid solutions, where you have a solid as your solvent. Metal alloys are great examples of this. Any jewelry that you are wearing would be an example of this. For example, my rings they look gold, and they are mostly gold, but there are other metals mixed in together with them. Otherwise, my gold jewelry would be too soft and it would not hold. It would not stay in a ring. It would just be flat. You can wear it. So that would be a solid within a solid. You can also add liquids and gases to solid solvents. Again, metal alloys are just mixtures of metals. And then there's a special type of this kind of mixture, which is called an amalgam. And let me find my cursor here. This term amalgam deals specifically with mercury. Because mercury, you guys know, mercury is a liquid at room temperature. And so there's a special form of solution with mercury, and we call those amalgams. And then you can have gas solutions. The air we breathe is a great example of this. Okay. It's pretty specific though. A gas solution, it has a gas as a solvent, and then the solutes are also gas. So still thinking about the idea of solvent as being the one that you have the most of. What that would mean is that with the air that we breathe, most of the air that we breathe is nitrogen. And so nitrogen is the solvent, and then all the other gases within that mixture, so oxygen, carbon dioxide, water vapor, etc., those are the solutes in that gas mixture, gas solution, I should say, be more specific. Okay. So a few words that revolve around the dissolving process that we need to make sure. I'm going to flip through a few of these slides just a little bit. One term to know is solvation, okay? This is the dissolving process in a solid and liquid solution. So what happens is the molecules of the solvent surround and separate the ions or molecules. So if you remember, we were talking about this, and I'm hopeful, let me come out of the presentation for just a second and draw on the board so that I can see you guys again. I'm gonna try to come to the board. I'm hopeful that the glare won't be too bad. I'll try to go in the corner too so that you can see a little bit better. But if I draw a beaker, you see that a little bit? This corner is hard. But there's my beaker. I'm going to fill it with water. Let's pretend our water is red. All right, there's our water line. All right, and then what happens, let's just take salt water. Remember, salt, NaCl. It's so hard when it writes backwards. So if you remember that sodium chloride that's sodium. I know it's backwards and I'm really sorry. I don't know how to fix it. I'm going to try. But sodium has a plus ion when it dissolves. Chlorine has a negative ion. When it comes into the water, it doesn't stay NaCl anymore. It breaks apart into its positive and negative ions. That's what we mean by solvation. I hope that is clear. Again, there's plenty of time to ask me questions, drop me a question in the stream or during my office hours. But let's go back to the notes again. So the molecules surround the different ions and help to break them apart. Hydration is the specific kind of solvation that we're talking about right now. I'm going to give you the example of sodium chloride because we're dissolving salt, sodium chloride in water. That's called hydration. Okay. Stay hydrated, my friends. All right, now, a few other terms. I know this is like English class almost because we do have to get through some terms. Dissociation, another term to know. This is when you have ionic compounds. The solvent molecules, meaning like in salt water, the water molecules would break up the crystals into ions. So again, that's why you would have all those sodium ions, those chloride ions swimming around in the water. Ionization, slightly different, a little confusing with terminology, but ionization is when you have a covalent compound starts to form some ions when they dissolve in a solution. So that would be like a sugar molecule, which is typically covalent. But because of the properties of water, for example, when it dissolves, it surrounds it and kind of basically forms covalent ions, which is a little weird to think about. Let me see if I can find let you know in your textbook. No, they just do sodium chloride, of course. Okay. Sometimes this is an endothermic reaction, and sometimes you have to talk about exothermic processes. So there's something called enthalpy, and we're actually going to talk about more enthalpy in later chapters. But there is something called the heat of solution, and that's how much energy gets exchanged during the dissolving process. So when you're dissolving salt in water, there's energy involved. When you're dissolving sugar in water, there's energy involved. So if you have a positive heat of solution, that's an endothermic process, which means it's bringing in energy from the surroundings. If you have a negative heat of solution, then it's exothermic, which means it's giving off. So a way to remember that is endo takes in, that prefix endo means into, exo like exit means to go out. And this chart is also in your book. You can see up here what's going on. You have a cube of something, whether that be sugar or salt. The energy content changes as it starts to break apart. So here you can see this cube is starting to break apart into its individual particles. That requires energy. And then it's going to give off energy as that solution starts being dissolved more. We're not going to worry too much about that process during this chapter. We'll deal more with the thermodynamics, which is what that's about, in the next coming chapters. Do you remember the term diffusion for the gases? The same thing happens with particles in solutions. The particles diffuse, whether it's dissolving in water or in the air. The gas particles diffuse throughout the air, or the crystal, like the salt particles, dissolve through the water, and they go from an area of high concentration to an area of low concentration. Okay, that's true in solutions. It's true when we talk about gases. It's true when we talk about solutions. Couple of things to remember, and there are things that we're going to talk about, and there are charts in your book that I'm going to refer you to. When you solve problems or I ask you questions, you don't have to memorize solubility charts. And there is a solubility table on page 313 in your textbook. So you can refer to that, page 313 in your textbook. It tells you some solubility rules. You have to read closely because there are exceptions pretty much buried within every rule. You don't have to memorize it though. You just have to use it as a tool. All right. So a general rule of thumb when you're talking about what dissolves in what is like dissolves like. So polar substances will dissolve other polar substances. Non-polar substances will dissolve other non-polar substances. Now, let me go real quick to this slide here. What does it mean when we talk about polar and nonpolar? Do you guys remember this? Maybe from a different science class? Or do you remember when we talked about the dipole moments? Do you remember that? When we talked about how water created a dipole moment? Where you have those electrons that want to be closer to the oxygen than the hydrogen. That creates a polar molecule. I hope you guys remember that a little bit. I don't want to go back through the whole thing. But anything that's polar will likely dissolve in anything else that's polar. Ionic compounds many times act like polar substances because they create that positive and negative charge that's attracted to the polar parts of the molecule. Okay. And the idea of solubility, the maximum amount of solute that can be dissolved in a specific solvent. And notice it says under specific conditions. What that means is things can change depending on the temperature and the pressure, kind of like the gases, right? So if you need to increase the solubility of something, sometimes you need to change the pressure or increase the temperature. And a lot of times that will allow you to dissolve more. All right. I know we're humming along with some terms. All of these are in your textbook. I would definitely encourage you, since I am not with you right now beside you, to answer some questions. Your textbook is full of information in chapter 12, the first section. So just as you know, the reason oil and water cannot mix is because water is polar and oil is nonpolar. That's why they are immiscible. Okay, that's why they cannot form a uniform solution. Again, going back to what I just mentioned, ionic compounds can dissolve in polar compounds because of those charged regions they create. There are some rules that aren't always followed, of course, the exceptions. So on page 313, just what I referred you to, you're going to have that chart available. You don't have to memorize that. If something is insoluble, it can't dissolve something else. It's not dissolvable in something else, I should say. This picture right here I'm going to show you is in your textbook. So what this is saying is it's starting with a sodium chloride crystalline structure, just like you'd pour from your salt shaker. It's in water. So our solvent is water. Our solute is NaCl. So look, do you remember how water is polar and it looks like the Mickey Mouse? Okay, so you have the negative oxygen and the positive hydrogen ends. Sodium positive, chlorine as an ion is negative. So look what happens. You take those positive sodium particles, they are going to get surrounded by the polar negative side of water. And then up here, because opposite charges attract, you have this negative chloride ion, and water orients itself, those molecules, to where the positive ends of those molecules are hanging out around the chlorine. And that's how those, the sodium particles and the chloride particles get dissolved in water. Those polar water molecules orient themselves so that opposites attract and the dissolving process takes place. Okay, now a few more terms. If something is unsaturated, that means the solvent can hold more solute. You can pour more in and it's still going to dissolve. A saturated solution, this one right here, means you cannot add any more solute. It will not dissolve anymore. So saturated, the solvent is holding all the solute that it can. Unsaturated means that you could add more. Now, all of this is at a certain temperature. All right, so again, if you increase the temperature, you're probably going to increase the solubility because as you increase the temperature, you're adding more energy, those molecules move faster, and things can dissolve a little bit more that way. Eventually, once you reach a saturated solution, you come to something called a dynamic equilibrium, which means, so you see this dissociation here, the sodium chloride dissolved in water dissociates sodium and chloride, but at the same time, it's going back. So you're going to get sodium ions and chloride ions coming back together and forming the crystalline sodium chloride, and then you're going to get the dissolving process at the same time. Back and forth, back and forth, back and forth at equal rates. Now, there is something called a supersaturated solution. And what that means is it's actually you've been able to create the conditions where the solvent is actually holding more solute than it should. That's supersaturation. So things that will affect how much will dissolve in a solvent, the temperature we've already mentioned, stirring, increasing the motion of the molecules, and how much surface area is exposed. So a lump of sugar has a harder time dissolving in a solvent than does sugar packets, like small crystals of sugar. If you increase the surface area of sugar that is exposed to the solvent, you're going to dissolve more of it. Okay, and again, I just kind of touched on this a little bit, but the higher the temperature, the more solute will dissolve. Okay. Just keep that in mind. When gases dissolve, it's usually exothermic, meaning they release heat. Okay, so heat is a product there. And the last thing in this section, I know it's been a long video, thanks for hanging with me, is the idea of how pressure affects solubility. And there's a law, and look, we're going to use some similar words that we heard with gases, directly proportional. The solubility of gases is directly proportional to the partial pressures of the gases above the solutions. So it looks very similar to some of those gas laws we looked about, where the solubility of one over the pressure of one type of gas is going to be equal to the solubility of the second over the pressure of the second. All right, that concludes the notes for section 12A. I know that was a lot. On Google Classroom, there is a classwork assignment that covers this section, okay? That is due Friday morning, all right? Now, we will have office hours. An email is going to go out, has gone out to tell you when those office hours are. I'll make sure that I am online during that time. And you can always ask questions. You can email me, of course, or you can post questions on the Google Classroom stream for our class. And use each other, talk to each other, text each other. But you can always contact me again, email anytime, or office hours. Okay, I'm going to stop this video now, and I will add another video for section 12B in a day or two.